I am Dr. John Bergduff. In this video, we're going to look at the future value of an annuity. What is an annuity? By definition, an annuity is a sequence of equal payments made at equal time periods. The future value of the annuity is the sum of all the deposits plus all the interest earned over a given period of time. Many times, students get the concept of annuity confused with general questions about compound interest. A typical compound interest generally involves one deposit that's made into an account of some sort and allowed to just sit there for a period of time, maybe years, and then at the end you see how much money you have. An annuity is different. In an annuity, rather than one single payment at the beginning, you make a number of payments, maybe once a month, for example, for a period of perhaps many years. A standard and probably the most famous example is a retirement annuity, in which perhaps through your entire career, you set aside a certain amount of money every month to have some future value you hope to have to retire on. In yellow, you'll see the formula for the future value of an annuity. And you'll see some familiar variables in the formula, but they don't all have the same meaning. P in this case does not stand for principal, as it often does. It stands for the periodic payment, how much you put aside every month, let's say. R is the nominal annual interest rate, or simply interest rate. N is the number of payments per year. T is the number of years. And A represents the future value of the annuity. Now, this formula is highly simplified. There are various assumptions that are made for this formula to work. First of all, the interest has to be compounded at the same time intervals as payments are made. That's not a really big one. The second one is a far bigger assumption. Interest rates do not change throughout the life of the annuity. Number three, payments do not change over the life of the annuity. And finally, number four, payments are credited at the end of each compounding period. The final one is more or less a technicality. The first three are very, very important. So let's take a look at how this works. Let's look at a specific example. I've repeated the formula here just for convenience. This is the classic example of an application of an annuity. At age 25, Jesus decides to start a retirement annuity in which he deposits $700 per month into an investment that returns 5% interest compounded monthly until he turns 65. How much will Jesus have when he retires? So in this example, you can kind of see how the formula really is rather simplified. Interest rates rarely stay exactly the same, and certainly not over a period of some 40 years. And as Jesus progresses through his career, he may find that he can put in more money. But this is a simple formula just to give us a general idea of how annuities work. Let's see what everything stands for. So we need to know P. P is his periodic payment. That's $700. R is the interest rate. This has to be expressed as a decimal, 0.05. 5% is 0.05. N is the number of payments per year. Notice that he is depositing money monthly and the interest is compounded also monthly. That is supposed to match, so that's a good thing. Monthly implies 12 times a year. T is the number of years. So he starts at age 25 and ends at age 65. 65 minus 25, that's a period of 40 years. And the future value is what we're trying to calculate. Over here on the right, I have a TI-83 graphing calculator, and I'm going to show that we can do this calculation all at once, basically entering exactly what we see. Starting with the numerator of the equation, of the formula, we start with 700 for a payment. Notice that we have two layers of parentheses, one square and one round. The graphing calculator doesn't actually have two shapes of parentheses. Well, we don't need them at least. So we're just going to use round ones twice. Open parentheses, open parentheses. 1 plus R, 0.05, divided by 12, close the parentheses. Then we need an exponent. We get an exponent using this button. Looks like a little hat. It's called a caret. And notice that the cursor moves up into the exponent. Older versions of TI calculators do not show you an exponent as an exponent. And in those cases, you need to make sure that everything that's in the exponent is included in parentheses. Just as a good practice, I always put everything that's in an exponent in parentheses, just to be safe. This would be n times t, 12 times 40, close off the parentheses that represents the exponent. Now I need to get out of the exponent. If I just typed in -1 right now, the calculator would think that I'm staying in the exponent. Use these little buttons here that form sort of a wheel, and use the one that moves you to the right. That will get you out of the exponent to where you can say -1, and then you close off this parentheses. So this represents the square parentheses. Now, all of that is divided by what you see in the denominator. So this is the entire numerator, and then click divide. And then the denominator is going to go in parentheses as well. Open parentheses, and it is R, 0.05 divided by n, which is 12. Close the parentheses, and we have now entered into the calculator exactly what we see in the formula. And if we hit enter, we will figure out how much money Jesus has as his future value, how much money he has when he retires. And this is a rather impressive amount. Let's write this down over here on our paper as well. So Jesus ends up with $1,068,214.11. That's quite a bit of money. Let's look at this a little bit more carefully with a follow-up question. Jesus had invested $700 per month over a period of 40 years, and he ends up with a total of $1,068,241.11 to retire on. How much of this income comes from the deposits he made, and how much comes from interest? So this is an interesting question. If we think about what Jesus actually has contributed himself, it's going to turn out to be a relatively low percentage of this. There's no specific formula. We just use logic for this. If he had been investing $700 per year and per month, sorry, and if he had been doing that for 12 months in a year and for a total of 40 years, 700 times 12 times 40 would be his contributions. Let's calculate that. So 700 times 12 times 40, enter. That would be $336,000. This is the total of all the checks that he wrote, or all the automatic withdrawals that he made over the course of those 40 years. That's quite a bit less than the 1 million plus that he actually ended up earning. All the rest of that is interest. His interest that he has earned, in other words, would be whatever the difference is between the $1,068,241.11, the difference between that and the amount of money that he himself contributed. Let's see what that would be on our calculator. That would be $1,068,241.11 $241.11. Don't want to forget that. Oh, I think I have a mistype here. Let me back that up. Sorry. $1,068,241.11. Sure I got that right? Yes. Minus $336,000. This represents all the interest that he had earned. The power of compounding you really, really see here, because he had earned a total amount of interest of $732,241.11, more than twice of what he himself had contributed. Pretty impressive. Thank you very much.